In 8.5, we're comparing linear, exponential, and quadratic functions. Our learning goal is I will identify linear, quadratic, and exponential functions using graphs or tables. So now you've gotten quite a bit of experience with the quadratic functions. We've already done linear and exponential. So now we're just looking at these three things, or we're looking at data, and we're determining if we have a linear, exponential, or a quadratic function. So just as a reminder, remember linear looks like this. It's a line. And our basic linear function was mx plus b. That was our slope-intercept form. Our basic exponential looked like this, where it curved and then it started raising or growing quickly. And that was the ab to the x. That was a curve. And then we also have our quadratics now. That our basic function looks like this, and we call that a parabola. And that has this general form. So those are the three things that we're going to be looking at today. So here I'm starting off with some points, and I want to tell whether these points represent a linear, exponential, or quadratic function. So in this case, it looks like I have only positive numbers here, so I can just draw this. And this goes up pretty substantially to 162. So let's make these maybe 20s. 20, 40, 60, 80. I probably could have gotten my 10s, whatever. 100, 120, 140, 160. And then I'm just counting by ones for my x values. Okay, so when I put in 0, I get out 2, which is going to be way down here. When I put in 3, I get out 54, which is going to be about there. Put in 4, I get out 162, which is going to be way up here. So you can see, even with just those 3 points, I'm growing really rapidly. 218 is going to be about there. 16 will be about there. So just looking at these, you can see I don't really have the parabolic shape because I don't have a vertex or an axis of symmetry in there. Instead, my points are just growing, 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 and you can imagine they'll just keep growing even faster and faster. So I would call this exponential growth. And then to check that, you can see if I multiply by 3, I get 6. If I multiply by 3, I get 18. Multiply by 3, I get 54. So actually my common ratio there is 3. So it's pretty easy to check just with the numbers as well. This next graph, it looks like I go between -3 up to 2. So this doesn't have to be a very big graph. Then I go all the way down to -9 at one point. So I put in -3, 1, 2, 3, I get out -9, 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that on the screen? Nope. When I put in 1, I get out -1. When I put in 2, I get out +1. When I put in -2, I get out -7. So if I look at these, it looks like they are lining up pretty nicely. When I put in 1/2, I get out -2. That would be right there. Yep. And if I connected those, that looks linear to me. And as you see, as I go from 1 to 2, I'm changing by 2. When I go from -3 to -2, I'm changing by 2. So my constant change here is a +2. So that's linear. Now, of course, if I had a collection of points that I graphed and they ended up making a shape, that looked something like this, then I would say that that's quadratic. So anytime they loop back on themselves, where I have symmetry here, in this section, that's going to be considered quadratic. Okay, I just stole this straight out of your book from page 437, but this is how you're going to determine whether or not you have a linear, an exponential, or a quadratic based on a table. So here you see that in each of these, my x value, I didn't label them, but my x value is always increasing by 1. So we're only going to be looking at the y values. If I look at the y value here, I'm adding 2, adding 2, adding 2. So we have a common difference, remember, of 2. So I'm adding the same thing each time. For every increase in 1 in my x, I'm increasing by 2 in my y. If I look at the exponential though, as my x's increase by 1, here I increase by 1, then by 2, then by 4, then by 8. So I don't have a common difference, but instead you can see pretty quickly that I'm multiplying by 2 each time. And remember, we called that a common ratio. So I'm multiplying by 2 every time. Multiply by 2, multiply by 2. So linear and exponential we've talked about already. Now let's look at our quadratic. One clue here is that I go from -1 to -2 back to -1. So it's like I'm going down and bouncing back up. So that's one indication that it might be quadratic. Another way to tell though is to look at the second difference. So up here we found that the first difference, or the first time we found like the difference between 1 and 3 is 2. The difference between 3 and 5 is 2. If I look at the difference here, I get from -1 to -2, that difference is -1. The difference between -2 and -1 here is I'm adding 1, so it's a positive 1. The difference between -1 and 2 here is I'm adding 3. Here I'm adding 5. So I don't have a common difference, but I don't really have a common ratio either. So this we call the first difference. It's the first time I'm finding the difference. What I can do is I can then look at the second difference, or the difference of the difference. To go from -1 to 1, that's adding 2. To go from 1 to 3, I'm adding 2. To go from 3 to 5, I'm adding 2. So here, my second difference is what's constant. And that's how I know it's a quadratic, if I find the difference of the difference and get a constant value. That's how I'm going to know. So when I look at a table, I just need to look at the difference of the difference. And we'll do a couple examples with that. Here I have two different tables that I want to determine if they are representing linear, quadratic, or exponential functions. So let's start off by looking at the difference. To go from 3 to -3, I am subtracting 6. To go from -3 to -5, I'm subtracting 4. So that tells me it's not linear because that's not constant, but I'm going to keep going anyway. To go from -5 to -3, I'm adding 2, and to go from -3 to +3, I'm adding 6. Now I want to look here to go from -6, oh, that shouldn't be -4, I was like, this isn't working. To go from -3 to -5, I'm subtracting 2. Sorry if I confused you there. So to go from -6 to -2, so this is my first difference, I'm sorry, I'm getting ahead of myself. My first difference was not constant, so it's not linear, but I'm also not multiplying by the same thing every time, so it's not going to be exponential. So to check if it's quadratic, I need to look at the second difference. So the difference between -6 and -2, I'm adding 4. To go from -2 to +2, I'm adding 4. To go from +2 to +6, I'm adding 4. So my second difference is constant, so this is quadratic. If I look at this table over here, I'm going from 1 to 3, which is adding 2, from 3 to 9, which is adding 6. This is adding a lot more than 6. It gets bigger and bigger. You could tell it's growing really quickly. If I looked at my second difference, that still wouldn't be constant, so this is going to be exponential. And I can tell really obviously that I'm multiplying by 3 every time. So that's the whole idea here. We also, though, are going to have to write functions based on these. So let's get into that. So here I have a table of values. I want to write a function based on this table of values. So first I have to decide, am I using quadratic, exponential, or linear? To go from -11 to -3, that's adding 8. -3 to 5 is adding 8. Here's adding 8, adding 8. So I can see pretty quickly this is linear, which means I'm using y equals mx plus b as my basic function. From here, you guys know how to come up with functions. I can find the slope by subtracting. So like I would do, I have a point 0, -3, and I have the point -1, -11. But I don't even really need to do that because I can see my change in y over my change in x. I'm adding 8 for every 1. So my slope is this constant difference of 8. And then remember, b is your intercept, your y-intercept, where x equals 0. So my b value comes from this point right here, 8x minus 3. That was super easy. So constant difference is your slope, and then your intercept came from that table. You could always plug a point in to find that intercept if it wasn't given to you, though, from the table. Now, where it can get a little trickier, though, is where you have to come up with quadratic. So the good news is we made life really easy for you. And let's see what we have. 0, 1, 4, 9, 16. So I have some data here. And let's look and see. I'm adding 1, I'm adding 3, I'm adding 5, I'm adding 7. That's not a constant, but it's also not multiplying by the same thing every time. So let's look at the second difference. I'm adding 2, adding 2, adding 2. My constant difference is what's the same. So this is a quadratic. Now, in the instructions in your book for this problem, they tell you to use the form, if it's quadratic, just y equals ax squared. So we keep it really easy. You don't have to do this if there's a bx plus c in there. So just using y equals ax squared, come up with a function for this. So what you can do is we just have to pick one of the points. We can pick any point over here. Let's pick this 4, 4. We're going to plug that in for x and y and solve for a. So y is 4, and that equals a times 4 squared. So 4 equals a times, what 4 squared is 16. Divide each side by 16. And I get that a equals, I ran out of room, a equals 1/4. So that tells me that my function is just y equals 1/4 x squared. So I just have to pick a point, plug it in for x and y to solve for a. And these aren't going to get any more complicated than that. You also have a similar thing then for exponentials that you've done earlier. So hopefully you're getting the hang of this and you can get to your homework. It is on page 439. You're going to do 1, 2, 10 through 24 even, 13, 25 through 30, and 31 through 34. This section really should be pretty easy. If it's not coming pretty quickly to you, you're probably overthinking it. So check with your teacher and just figure out, what part you're not quite getting, because it should, like I said, should be pretty easy. This is one of the easier sections in this chapter. So good luck.